Hi everyone, my name is Junjian from China University of Petroleum, Beijing. Now I'm visiting at SINTEF Digital in Oslo. I'm very glad to have this opportunity to give a topic about the near-wellbore modeling for vertical wells and its application in water control operations. My slides can be divided into 4 parts. The first part is about the background. As we know, water flooding is the most widely used development strategy for oil field worldwide. However, the water is easy to channel and the water shutoff operations are required. According to the statistics, only half of the water blocking operations are successful. One of the important reasons is that lack of scientific and accurate numeric simulation method. Usually, for chemical water shutoff operations, only 10 to 100 cubic meters of chemicals are injected into oil wells, which is very small compared to the reservoir volume. And standard simulation and numerical simulations are often aimed at large scales, which is incapable of describing small-scale flow of water control process. There are two main problems in simulating such a small injection volume. First is about the numerical dispersion. The simulated water cut drops always much smaller than the real one. Another is wellbore flow description. And the flow modeling of the agent inside the wellbore is absent. So the injection parameters, such as injection pressure, and that the production engineering concerns cannot be obtained. We have compared some of the commercial simulator. Current commercial simulators are difficult to meet the requirement of water control flow simulations. For example, for the Eclipse near-wellbore model from Schlumberger, it has the detailed near-wellbore flow, but it's quite hard to couple the wellbore flow. For the Night tool from Halliburton, it can model the detailed wellbore flow, but there is no high-resolution near-wellbore flow. The MRST Near-wellbore module provides flexible and scalable framework for hybrid grading and simulation of horizontal wells. It used 4 kinds of grid, from large to small, to realize near-wellbore characterization of horizontal wells. But the model of vertical wells is absent. So the objective is to develop a near-wellbore modeling method for vertical wells under the framework of near-wellbore model that initially implements the near-wellbore modeling for horizontal wells. The second part is the near-wellbore grading for vertical wells. The arrangement of the vertical subgrade are the same with the horizontal subgrade, and it all has the corner point grid and the unstructured grid, the radial grid, mostly intersects in the wellbore grid. Yeah, but the geometries are different. Unlike horizontal wells, the near-wellbore grading for vertical wells performs in Z direction. The layer of well grade is non-uniform to conform with the vertical trajectory. The well trajectory is constructed from a series of discrete well points entered by the user, which may represent important features such as the packers, the downhole tools, and interlayering, etc. Therefore, each subdivision layer of the vertical well grade must correspond to each well section. A layer may contain multi-uniform well sections. In order to make each subdivision layer of the well grid, the density of the well grid in the longitude direction is non-uniform. Here we design a new method to calculate the intersection point of the well. The intersection factor of the layer is determined by the distance well to the upper face. After finding all the input well points and intersections located within a certain green layer, we can determine the interpolation coefficient of the refinement layer based on the distance from the point to the top surface of the layer. Thus, we can obtain a non-uniform, refined, unstructured grade, as shown on the right. Horizontal well grades are constructed along the Z direction, while vertical wells grades are constructed along Z direction. So the construct of Cartesian 2D grade is a little different from horizontal wells. This Cartesian grid is still generated by the function of horizontal wells by constructing a vertical horizontal well trajectory. The vertical trajectory is centered on the projection of vertical wells on the XY plane that extends along the x-axis. For the radial grid along Z direction, the vertical radial grid is built inside the structure region of VOI along Z direction. The properties are collected along the Z direction, such as the permeability, porosity, cells, faces, nodes, and boundary nodes. And the gradual circular radial grid is supported for vertical wells, whose angular length gradually vary from the circular line to the rectangular line. And the circular line is the pressure potential line. It can avoid the low quality of irregular cells of circular radial grid. And the most inner part is the tailored wellbore grid. And the wellbore grid is built inside the inner void region of the radial grid. Two types of wellbore grid are built for different well settings. The first type is single ring grid. It's usually used for production ring or general injection stream. There is only one tubing inside the wellbore. Another we call the dual ring grid. It usually used for target the injection stream. There are two tubing inside the wellbore. Between these two tubing, we can place several packers inside it to prevent the analogous flow in the tubing. Then we can decide the connectivity of the wellbore grid nodes by the flow patterns and well structure. For example, for the dual ring grid, and there is a two tubing inside the wellbore, and there are two packers, and between the two packers there is perforated, so the injection of the chemicals can flow from the perforation into the reservoir. So we can give the connectivity for the packers and for the two tubings. For the cooled part, there are only two new grading workflow class for the vertical wells was built, and almost the same with the horizontal wells. There is without much modification, which benefiting from the near-wellbore scalable grading framework. And the third part is near-wellbore simulation for vertical wells. The workflow class to generate data structure passed to MRST AD simulator for horizontal hybrid grid to fully compatible to vertical hybrid grid. The pressure drop models are defined for two types of wellbore. For the single ring wellbore grid, the flow type including radial inflow to the reservoir, axial flow inside the pipe, and axial flow inside the pipe with different compilation method. One for open hole compilation, one for perforation compilation. And we give the pressure drop by the correlations. Here is the correlations for different part. For the two ring wellbore and the flow type including radial flow to the reservoir and from reservoir to the annulus, radial flow from annulus to the tubing, and axial flow inside the tubing. And this is the correlations for water injection. And we can also give the formulations for chemical injection. And most of the production engineering concerns the injection pressure for the wellhead. So the wellhead injection pressure should consider the plugging agent flowing the pipe stream from the wellhead to the top of the oil layer. We can calculate the well pressure according to the different flow regime. This is for laminar flow, for turbulent flow, and for transit flow have different equations. And this is the last part of the applications. We have compiled a module interface for water shutoff, including all the decision-making process. We can import the Eclipse data set on the interface. And after the import the Eclipse data, we can perform flow diagnosis to determine the connectivity between the wells. Then we select the well candidates to determine the VOI. We can determine the VOI by just clicking on the mouse. The meshing with their VOI to determine the injection type and production stream type and conduct water plugging simulations. This is a simulation result. The agent can be agent injection process in the ball reservoir can be computed. And as the picture, we can see first the chemical agents are injected in the tubing, then slowly inject to the reservoir. The key parameters that production engineering concerns can be optimized, such as injection pressure, injection rate, blockage radius, and plug size. And the reservoir permeability is really specified according to the agent distribution and residue resistance factor. The production performance of the control can be computed with the production stream. This is a real field application. We apply this in China's Jiang oil field. And first, we import the Eclipse data of this reservoir. Then we calculate the well connectivity by flow diagnostics. There are 4 well groups in this reservoir. For each well group, there is a producer with very high allocations with the injector. So we select this kind of well to be the candidate for water shutoff. Then we calculate the drainage volume of flow partition, and we calculate the water control potential for the 4 selected wells. Combined with the water cut, last we decide these 4 wells will be the candidates for water shutoff. For each candidate, we make grading for the target wells. This is for NP 12 to 183. This is for NP 12 886. Then we can make optimization for the injection rate and the injection pressure. After that, we got the performance prediction for each wells. So the last one is conclusion. And the functionality for MRST Near-wellbore model has been improved for supporting more well types, chemical wellbore flow, and complex well stream. We have compared the MRST Near-wellbore model to use the standard simulation, Eclipse Near-wellbore model, Eclipse coupled with the net tool, that it shows that for the MRST Near-wellbore model, it can model the high resolution near-wellbore flow. We can simulate wellbore flow with oil, water, gas, and chemical agents. It can simulate the complex intelligence well stream. And we think it can be extended to the simulation of other single well operations that requires detailed description near the well. It links the reservoir engineer and the production engineer, and bridging the gap between reservoir and the production engineers. Thank you for listening, and thanks to the MRST group. I have been visiting SINTEF for almost 3 months. I quite enjoy staying here, and hope something better can be created in the future.